Hello, good evening. This is going to be lecture 1 on abstract algebra. And so today we will be, if you look into the syllabus of abstract algebra, so we have group theory, subgroups, abelian groups, non-abelian groups, cyclic groups, permutation groups, which are very easy, normal subgroups, Lagrange's theorem for finite group, which is a very important theorem. Then we have group homomorphisms and quotient groups. Then we have rings and subrings. And then we have ideals, prime ideals, maximal ideals, a very small topics on rings and ideals, and a very small part of fields. Okay, so let's get started with the first thing, that is the definition of groups we are having. So if I go to the first slide, so we have the definition of group here. Now, if you look into it, what is a group? So group is a set of conditions that are defined on a set G. So we are having a set G. On that, we are defining a set of conditions. And if those conditions are satisfied by the elements of that set G, we say that that set defines a group. So for defining a group, we take the set G. And on that set G, we define a binary operation, which is star. Okay, so what is a binary operation? It is an operation, it could be addition, it could be subtraction, it could be multiplication. So these are the basic operations that we take. It could be division of two elements of that set G, or it could be any other operations for like A plus B minus C. So if you are talking about A star B, we are talking about A plus B minus AB. We can talk about in that way as well. So this binary operation star could be any operation, but this operation along with the elements of set G must satisfy these conditions. What is the first condition we are having? That means what? If we are taking any two elements, that is A and B of the group G, and if we take the closure of these elements, that means what? If we apply the binary operation on these two elements of the set G, the element we will be getting, or the resultant element, say suppose C we are getting, we say that if this C is in the set G, then we say that the closure property is satisfied by the elements of set G. But we cannot yet say whether this set is a group or not. It should satisfy other three conditions. The second condition we have A star B star C. That means what? You perform the operation on these two, and then you perform the operation with the other. Okay. Similarly, it should be equal to you perform the operation on the second two, and then you perform it on the first one. That means if the associative property is satisfied, in that case, we say that the set is associative. That means what? So we have till now satisfied two conditions. The first one we have done is for the closure. The second one we have done is for the associativity. Now, if we look into the third one, is that we must have an element E such that if this element E is taken, is operated with the element A, it could be any element we are talking about, that is for all A, and that is equal to, if we like commute it, like if we do it A multiplied by B, or you can call it the binary operation E, is equal to E into A. If this happens and this is equal to A, and this is for all A belongs to G, if this happens, we say that we are having an identity element in the group G, and that element is nothing but the identity E. Okay, and there's one more very important thing that we will study later, that E is unique. Right? If we are able to prove that this set G is a group, then in that set, this identity element E has a special name because it's a unique element for this set G for the operation. Okay, so this is specified for this operation. So if you have fixed that the operation we are performing is this star operation, then in that case we can say that this identity element E is the unique element for G. Okay. And the next one we have is the inverse property. That means what? No matter whatever element we take from A, we must always get an element B, such that if we take the closure of A, like if we take a particular element A, we are going to get another element B, such that if we take the closure of A by B, on the closure, it's a binary operation of A by B is equal to B by A is equal to E. That means what? We are getting an inverse element in the group, and this inverse element is unique up to the element A. So if, for example, if we change this element A to say A1, then this particular B will not work. We will get another element B1, for which this will be equal to E. So they are saying that this element must exist. Okay. So if these four conditions, what are the four conditions? We have the closure, we have the associativity, we have the existence of identity, and we have the existence of inverse. So if these four properties are satisfied by the group G or by the set G, in that case, we say that this will form a group under the operation, which is the star operation. There is also an element, that this E element we are talking about, it is known as the identity of the group. And what is meant by the identity I was talking about is that A star B is equal to B star A is equal to identity. So this E is known as the identity, and this B element which we are talking about, this B, by which if we take the product or if we take the binary operation with A, gives us identity. This B is known as the inverse of A, and it is also written as A inverse. Now we have that if suppose we are talking about a group G, this group G is said to be an abelian group if we have A star B is equal to B star A. That means what? A binary product with B is equal to B binary operation with A for all A comma B belongs to G. In that case, we say that the group G is abelian. Okay. So till now we have understood what is the definition of group. Now let us see few of the examples of group. Okay, so there are a few more property, that is the distributive law. So we have A multiplied by B plus C is equal to AB plus AC. So this is known as the distributive law, which is satisfied for all the elements of Z, right? Let me see. Yeah, let us see a few examples based on it. First example we are having is the Z, and we say that Z is said to be closed if we are taking the set of integers. And if we look into the closure or the multiplication, so we can simply say that if we add any two integers, that will always be an integer, right? And simply if we multiply any two integers, that is also going to be an integer. So from here we can say that the set of integers we are talking about is closed under the addition and multiplication. So we can say that the first criteria is satisfied. So we are talking about two binary operations. The first one is addition and the second one is multiplication. Now, if we want to talk about the associativity, we can also say that the addition and multiplications are associative as well. Right, we can write A plus B plus C no matter where we put the brackets. It's always possible, right? Furthermore, if we talk about the commutativity as well, we can simply say that A plus B will always be equal to B plus A, and similarly AB is equal to BA. So from here, we can also say that addition and multiplications are commutative. So till now, we have closure, associativity and commutativity with respect to two binary operations on Z, that is addition and multiplication. Okay, now let's move and see few more. Now, if we talk about the distributive property, the distributive property is not yet required in the case of groups, but we can see what are the properties that are satisfied by the elements of Z. So we have that A multiplied by the B plus C. This product is distributed over addition. So we have A multiplied by B plus A multiplied by C. No matter whatever A, B, C we take in Z. Now, if we talk about the identity element for Z, so additive identity is 0. That means what? No matter whatever integer we take and if we add it to 0, we will get the same integer, right? Similarly, the multiplicative identity is 1. So that means what? No matter whatever element we take, and if we multiply it by 1, we will get A itself. Right, so these are the properties we have. Now, if we talk about the inverse, so till now we have four properties. The first one we have proved closure, the second one we proved associativity, and the third one we proved abelian, the commutativity. Commutativity is also known as abelian property. The fourth one we proved additivity and multiplicative identity. The most important one is the inverse. So inverse means what? If we add any element, say a blank element, to A, we must get a 0. So the only possibility is what? If we add A minus A to A, we will always get the element 0, right? So in that case, we can say that minus A is what? It's a additive inverse, okay? Now, if we talk about the multiplicative inverse, in that case, we take a element A and we must have an element, other element, which will be equal to 1. For example, if we take 3, which number should be multiplied by 3 to get 1? Obviously, it should be 1 over 3. But if you look into this properly, this 1 over 3, 1 by 3 is not an integer, right? So in that case, we can say that the number 3 does not have an inverse, right? A multiplicative inverse. So from there, we can say that we don't have multiplicative inverse for all integers. So we may get a multiplicative inverse for a few integers, but we won't get multiplicative inverse for all integers. So from here, we can say that it will form a group. So if we go to the next page and see, there's another example we are having. So we from here, if we talk about it, we can say that if we have A belongs to Z, we don't have an element B such that A be equal to 1. So from here, we can say that this Z we are talking about will form a group with respect to addition, but it will not form a group with respect to multiplication. And why will it not form a group with respect to multiplication? Because we don't have a multiplicative inverse inside in the Z, right? But if we talk about the rationals, the reals, or the complex, we can see that every element other than 0 has a multiplicative inverse, right? So if we talk about the set Q, we will always get a multiplicative inverse of the elements. But if we talk about the 0 element, this won't have a multiplicative inverse in it. Similarly, if we talk about the reals also, it also have multiplicative inverse of all the elements, but 0 will not have a multiplicative inverse. So if we are talking about the group that we can form with respect to multiplication, we can simply element 0 from R, simply element 0 from Q, and this set, if we talk about the multiplication, will form a group. Okay, similarly for the C also we can do the same thing. So this is the most important example, our most fundamental example in group theory. Let's move to the next one. So next one, we first need to understand what is the mean by integration modulo or congruence classes. So for that, let us take n to be, which is greater than equal to 2, is an integer. The set of integer modulo n, or it is denoted by Zn, which is what? It is a set of all equivalence classes of Z. So if you have studied about equivalence classes, it's very good, or else we will look into here how to find equivalence classes of Z. That means what? We have the relation A congruent modulo B mod n. We call this congruence classes modulo n, and we can define Zn to be of these type. So for example, if you talk about the elements of Z4, so the elements of Z4 is what? You have two elements, A minus B, which if you divide by 4, it is equal to 0, or it is equal to 1, right? We can say that it is divisible by 4. So we have two elements which is divisible by 4. That element is known as Z4. If we talk about the 0, 0 is the collection of all those elements. When they are divided by 4, the remainder is 0. Okay. Similarly, 1 is the collection of those elements which are if are divided by 4, the remainder is 1. For example, -7, -3, 1, 5, 9, and so on. Similarly, this 2 is the collection of all those elements which when divided by 4, the remainder we are getting is this -6, -2, and so on. Similarly, for 3 is the collection of those elements which when divided by 4, the remainder we are getting is 3. Now, when we are dealing with equivalence classes, these are the representative of the class. It are not unique. So this 0 class can also be known as 8 class. This is also known as -4 class. This is also known as 4 class. So that's what they are saying. The representative of the class is not unique. The 0 class can also be represented by 8 class, which is also be represented by -4 class. Right? Yeah, that's what they're saying, that we could simply easily have written -7 or -5 for this particular class, for one class. Instead of if we are talking about the 3 class, we could write -5 class, -1 class, -7 class, and so on. It will reduce the final answer in Zn to form A. So, but we do it very easily, that we reduce the final answer to the smallest representative and introduce it by 0. So similarly, it is the fundamental we are having. We introduce by 0. This is 1, this is 2, and this is 3. We can now define addition and multiplication on Zn. So this is for the Z4. We have 0, 1, 2, 3. We are talking about Zn. We have this, that is a box A plus box B will be equal to the class A plus class B can be written as class of A plus B. Similarly, class A multiplied by class B will be represented by class AB. Now, if for example, if we look into Z7, we have class 5 plus class 2 will be class 7. Now, if we divide 7 by 7, we get the 0, right? So this is a 0 class because 7 is divisible by 7. So that's why it belongs to a 0 class. But if we multiply 5 by 3, we get 15. Now, when we divide 15 by 7, we get the remainder of 1. So it is represented by 1 class, okay? So similarly, there are few of the properties of the classes. For example, if we have 3 classes, say A, class E, and class B in our Zn, Z modulo n. So we can also define, with respect to multiplication, we can define the closure. That means what? The product of any 2 classes in Zn is in Zn. We can define the associativity. We can define the commutativity as well. That is, class A multiplied by class B is equal to class B multiplied by class A. And we can divide the distributive law as well. Class A into class B plus C is equal to class A into class B plus class A into class C. We can define multiplicative identity as well. Class A into 1 is equal to class A. Now, from here, we can say that Zn, if we're talking about the Zn, we can see that with respect to multiplication, if we talk about with respect to addition, we can satisfy all the 4 properties. That is what? Class A plus class B. It is what? We have seen that it is class A plus class B. And this from here, this also belongs to Zn. So the closure property is satisfied with respect to addition. Now, if we talk about the associativity, class A plus class B plus class C, it is equal to class A plus class B plus class C. So from here, we can say that associativity property is also satisfied. The third property we have is identity property. So we must have class A plus some other class, which gives us class A. So what we can have it in this way: class A plus something is equal to class A, right? So we can simply have class 0. So from here, class of A plus 0 is equal to class A. So from here, we can say that the 0 class is the identity class. Now, what should be added to class A to get the 0 class? Well, obviously, we should add the minus A class to get 0 class. Now, minus A class can also be written as N minus A class, okay? So from here, if we talk about the addition, with respect to addition, it forms a group, okay? For example, 0 is the identity and N minus A is the inverse of A, okay? But if you're talking about multiplication, we haven't seen whether in order to multiplication, we can simply say that there will be a identity element, but we are not very sure till now whether we are going to have inverse element, right? So let's see what we can do about multiplication. Okay, so here we have, like, before moving into multiplication, let's see the table. Okay, so if G has finitely many elements, we can represent it by a group table. For example, there's a group table given to us. We are in the first column, we have 0, 1, 2, 3, 4, the elements of Z5. Z5 will have 0 class, 1 class, 2 class, 3, and 4 class. Okay, now if 0 class is multiplied by 0 class, we will, so this is an additive group, right? So if we have 0 class is added to 0 class, we will always get a 0 class, right? Similarly, if 0 class is added to 1 class, we will get 1 class. 0 class is added to 2 class, we will get always 2 class, and so on. Similarly, 1 class is added to 0 class, we will get 1 class. 1 class is added to 2 class, we get 2. 1 added to 2, we get 3. 1 added to 3, we get 4 class. And if we get 1 class added to 4 class, we get 5 class. Now 5 class can be written as 5 minus 5 class, which is nothing but the 0 class, right? In the same way, we can do the same for the other ones as well. And from there, we can derive this additive group. We can derive the group table of this group. Okay. Now let's see. Okay, now here we have seen that in the previous step, if you talk about the multiplication, for example, if we talk about the set of non-zero rational numbers, which I have already told that if you subtract 0 from the numbers of rationals, we will always get a abelian group. Now, what is abelian means? You take any two element and multiply two elements of the rationals, it will equal to b into a. So we can define it in this way, right? We can also see that the product of two non-zero rational is a non-zero rational. So now the question may arise whether if we subtract 0 from the group of rationals, will it be closed? So we always know that if you multiply any two rationals which are non-zero, obviously you will get a number which is non-zero, right? We have A cross B is equal to, we want it to be 0, so it is not possible, right? Yeah. So from there, we can say that now if we're talking about the multiplication of rationals, that is both associative and commutative. So from here, we can see that. And if you multiply A by 1, we will get A for all A belongs to G. So A is the identity element. Now, if we talk about A, suppose we have m by n. So if you're talking about inverse, the inverse will be n by m, right? So that m by n getting multiplied by n by m, that will give us 1, right? This last example is a second look. So from here, we can say that if you're talking about this non-zero integers, okay? So if you want to find whether the non-zero integers forms a group or not, this is not possible, right? For example, if we want to find the inverse of 2 in this, that should be equal to 1 by 2, right? So from there, we can say that only 1 and minus 1 are having multiplicative inverse for the integers. But this is true if we take out the number 0 from the rationals, that will form a group. But if we take the non-zero integers, that is not going to form a group. Okay. Now here we have, suppose we take the integers. Now since we have seen that if we are talking about Zn, this forms a group with respect to addition, but we are not sure whether it forms a group with respect to multiplication or not. So in order to do that, if we take the integers, so in order to say that, suppose we have the class A and the class B. So in order to have it to be class 1, we should have class A is equal to 1 over class B, right? Right. So from here, this will not be possible because we're talking about integers. So this kind of elements will not be in our integers. So from there, we can say that this doesn't form a group with respect to multiplication. But what we can do is, for example, suppose we have our element A is in Zn, and we form a group Un, which is a collection of all the elements for which we have GCD of A comma N is equal to 1. So in that case, if you're talking about U10, so Z10 will have elements like what? It will have 0 element, it will have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this will have these many elements, right? Now, if you're talking about the U10, which is will be what? GCD of all the elements, which is prime to 10. So which elements are prime to 10? We have 1, we can take 1, we can take 3, we can take 7, and we can take 9, right? So these elements will be in our U10. And if we look into it properly, this will form a group. That means what? This will form a group with respect to multiplication. So from there, we can form the multiplicative group as well. So 1 multiplied by 1, which is 1. 1 multiplied by 3, which is always 3. 7 multiplied by 1 is 7. 9 multiplied by 1 is 9. The 3 multiplied by 1 is obviously 3. 3 multiplied by 3 is what? 9. And 9 is in the group, so it doesn't matter. Now we have 3 multiplied by 7 is what? 21. Now since we are talking about the multiplicative, so we will divide 21 by 10. And if you do that, you get it to be 1. So from here, the element is 1. Similarly, 3 multiplied by 9 is what? 27. And if you divide it by 10, you get 7. So from there, if you look into it, all the possible values, you can say that U10 will form a group. Okay. Now here we have the last example is that the collection of all the complex numbers for which W to the power N is equal to 1. Okay. Now, since this will form a group or the abelian group with respect to multiplication, for example, if you have V into W to the power N, this will be equal to what? V to the power N, W to the power N, which will be equal to 1. So this will form a closure we are getting. We will also get an inverse element in the group. So we have 1 over W to the power N is equal to 1 by W to the power N, which is equal to 1. Now, if we talk about N equal to 4, so for here we have W to the power 4 equal to 1. So what are the possible values of W we will get? 1, minus 1, I, and minus Y. And this will form a group. This is also known as, now if you take N equal to 1, so for that we will get W equal to 1, which contains only one element, and that will be the trivial group. Okay. So that's all for today. In the next class, we will talk about few of the other properties of groups, and we will look into few of the various types of groups. For example, we will talk about order of group and see how the order of group affects the properties of group. Thank you for today.